Hi, my name is Jason and my partner is Matthew. And our presentation will be on two-port networks featuring the Y matrix. The topics that we will discuss is first the definition of admittance and its units, followed by the Y parameter formula, then how to solve for the Y parameter matrix from a two-port system, followed by two examples, the first being how to solve for the Y matrix from a two-port linear network, and then two, how to draw that Y matrix into an equivalent circuit in a larger system to solve for an unknown value. Lastly, we'll be discussing the Y parameter uses and applications in the real world. What is admittance? By definition, admittance is how easily a circuit or device will allow current to pass through it. It is the inverse of impedance, and admittance is also a complex number with the units of Siemens. The historical unit was the mho. Being a complex number, we have G plus the imaginary number times B, where G is the conductance and B is susceptance. Admittance is also a function of frequency, and this table shows the RLC elements, their impedances, and the equivalent admittance formula. The base units of a Siemens is 1 second cubed times ampere squared over kilogram times meter squared. And being the unit of electrical conductance, 1 Siemens passing through a device means that 1 amp will increase per every 1 volt. Here is the Y parameter formula, where I is the current matrix equaling Y the admittance matrix times V the voltage matrix. The parameters of Y11, Y12, Y21, and Y22 are the admittance parameters. And in the picture of the bottom right, we see the relationships between I, V, and Y. Here in the admittance triangle, we see that the admittance is the magnitude by adding the conductance and susceptance, and also the inverse of impedance. It was first coined by mathematician Oliver Heaviside in 1887, where he was a great contributor to other maths and science topics. The general method on how to solve for the Y matrix is to first let one port equal 0, let's say port 2, and we do this by short-circuiting that port. And when we do that, it leaves these terms with 0. Then we can solve for the individual parameters of Y11 and Y21. Subsequently, letting port 1 V1 equals 0 by short-circuiting that port will make these terms go to 0, ultimately solving for Y12 and Y22. The summary based on these manipulations show that we can solve for each parameter by letting the two-port network have two separate conditions of when port 1 equals 0 or port 2 equals 0, and doing so is by short-circuiting them for the Y matrix. The names given for these parameters is the input driving admittance for Y11, the forward transfer admittance for Y21, the reverse transfer admittance for Y12, and the output driving admittance for Y22. Once we've solved for our Y matrix, these parameters can be drawn into an equivalent circuit shown here, and we notice that all elements are in parallel, and that we also have a voltage controlled dependent current source seen as Y12V2 and Y21V1. From here we can take it into a larger system to solve for a value in question. Matthew will then discuss these two examples ahead.
Here we have a circuit that was created in LT-SPICE so that the derivation of the four significant values of the Y matrix, Y11, Y12, Y21, and Y22 can be found. In this example, the process is started by shorting the right side of the circuit, making the R4 resistor irrelevant. As the shorted port 2 will be the path of least resistance, and also adding a power source to the left, which will be shown on the next slide. And then at this point, I1 and I2 can be determined, which will allow for the calculation of Y11 and Y21. Then the opposite is done. The left side of the circuit will be shorted and a power source will be added to the right side, allowing for the other two figures to be found. So here is what was just described with the right side being shorted. The R4 is not present, and we chose a 10-volt power source to be added. And with that, basic mesh analysis was carried out, and as you can see, we did this in a clockwise fashion, just following one example, I1 here. The power source is entered from the negative terminal, resulting in negative addition. The 2 ohm resistor multiplied by I1 and the difference of I1 and I3 times the 4 ohm resistor. Same approach with I3. With these two equations calculated, I1 and I3 are found, and thus so are Y11 and Y21, being the I1 over V1 and I2 over V1, shown here. This exact process is then carried out with the power source on the opposite side. Due to the configuration of the circuit, though, there's no resistors deleted. To avoid a little bit of redundancy and to capture the most important point, when these three mesh equations are found and calculated, we get all the currents that we need to come up with Y12 and Y22, again being just I1 divided by V2 and I2 divided by V2. And at this point, this circuit that we had shown, we have the four values that are known as the Y matrix or the admittance matrix. And those values are shown right here. Y11, Y12, Y21, and Y22. Here in example 2, this is just an example of how the newly represented circuit that we just found can be applied to another circuit to see how the current is going to react. And then this is the representation of the Y matrix shown earlier, with Y11 in parallel with a dependent voltage source. And this is our second example right here, our second circuit. And when you take the configuration that we just shown with the values that we previously calculated, When you apply this new circuit, you can see that with just some quick mesh, you can come up with IB here, which would be the reactant current of this 2-port being added. And again, just clockwise fashion, going around 120. 2 times the current, the difference of I1 over I2 times 4. Repeat the process. And then just simple Kirchhoff's current law. And then here, the admittance matrix, the Y matrix, is often used for different filter combinations, in particular designing networks with matching impedance. And the purpose to match the impedance can be applied for finding max power transfer between a source and a load, as well as correcting power factors. And these would just be some examples of some matching impedance networks. And this here is a list of the websites where we gained what we were able to find out. Thank you.